Hey, Physics 2011 students. I wanted to post one additional problem that involves energy conservation when you have a non-conservative force, just to kind of flesh out your available example problems that you can look at. So some of us were able to, we talked about this in some of the sessions, but not all of the sessions, so I wanted to make sure that you had access to that. Um, so this problem, a skier problem, it's similar to one that's in the homework. A skier starts from rest and slides down a 28-degree incline. So think of theta equaling 28 degrees, and we have our skier here. And the length of the incline is 85 meters. And let's see, theta is 28 degrees. And it asks us if the coefficient of friction, mu k, equal to 0.09. What is the speed at the base of the incline? So v here equals what? That's for part A. And then part B is asking us, if the snow is flat at the foot of the incline and has the same coefficient of friction, how far does it go? So part B is asking us, how far does the skier travel? And we're doing this with energy conservation. So this problem is a good chance for us actually to review how friction works on an incline too. So it's a pretty good problem. Let's assume that our coordinate system y equals 0 is at the base of the incline. That's probably the most kind of intuitive way to do this, but as you know, it doesn't have to be that way, but let's set it up that way for this. And then let's state our energy conservation expression. So the initial mechanical energy, potential and kinetic, is going to equal the final mechanical energy plus any work that's gone into, that's been done by friction. So the potential energy, there is no initial kinetic energy because he's starting from rest. And then at the bottom of the hill, there will be no potential energy because it will be at y equals 0. So because v equals 0, because y is 0. And so we're left with an expression that just says that the potential energy initial has to equal the kinetic energy final, or at the base of the hill, plus the work that's been done by friction. So normally we think of potential energy as mgh, and our kinetic energy as 1/2 mv final squared, and the work done by friction. So a couple details. What is h exactly? Well, h, we are not given it directly, but we are given d and we are given theta. So h will be d sine theta, this side of the triangle. What is the work that's done by friction? Well, let's break this down. So the work done by friction would be the force of friction times d times sine theta, or cosine theta rather. And the force of, so let's flesh out our free body diagram here. We have our skier. He would have force of gravity that would be pointed down. There would be a component of that that would be perpendicular to the incline. There would be a component of that that would be along the incline, thinking back to our incline plane problems. There would be the normal force, perpendicular, and then the force of friction. So the work done by friction is going to be the force of friction times the displacement. The force of friction and the direction are anti-parallel, so it'll be negative, but we know that, and that's incorporated in our signs because we know that work is going to be, that energy is going into the work that's done by friction. In other words, the sum of the kinetic energy and the work done by friction will equal the initial energy. The kinetic energy, therefore, has to be less than the initial potential energy because some of the work has gone into friction. And so we can calculate this work. It'll be the force of friction, which will be mu k times the normal force. The normal force in this situation Remember, the normal force is just equal to mg cosine theta because you're not accelerating in the y direction. So this will be mu k mg cosine theta times d, and that'll be our work done by friction. So let's add that ingredient in down here, mu k mg cosine theta d, and let's put everything in and solve for v. So mg d sine theta minus mu k mg cosine theta d is going to equal 1/2 mv squared. Notice the mass cancels. It appears everywhere. We could factor out a factor of gd from both of these terms and solve for v. And what would we get? We would get that v is going to equal, so we would have gd times sine theta minus mu k cosine theta times a factor of 2, take a square root. And we can put our numbers in here. So v would be 2 times 9.8 times 85 times sine of 28 degrees minus 0.09 times cosine 28 degrees. Take a square root of that whole situation, and you would find that the speed at the bottom of the hill would be about 25.5 meters per second. So that's the first part of this question. And then we can think about what's happening at for part B. Now that you have the velocity at the bottom, what's going to be the work? How far are you going to go? So maybe it would have been better to think of this as from A to B and from B to C. So this would be the potential and kinetic energy at A is going to be equal to what's going on at B, and then the kinetic energy. Well, let's just set it up. The kinetic energy plus potential energy at B is going to equal the kinetic energy plus potential energy plus work done by friction at C. I'll just put work friction on flat. So check it out. There's not going to be any initial potential energy at B because it's already at the bottom where y equals 0. There will also be no potential energy at the end. There will also be no kinetic energy at the end because it comes to rest. Y equals 0, V final equals 0, y equals 0. So we're left with just that the kinetic energy at B has to equal the work done by friction on the flat. And this is easier because the normal force on the flat is just equal to the weight, mg. So we can set this up. We would have 1/2 m, we call it vb squared, is going to equal mu k times mg, so that's the force of friction, times the distance. And notice again the mass would drop out, and we would be left with, we're looking for d, we would just solve this for d. D would be 1/2 vb squared over mu k times g. That's our expression for d. We can put our numbers in. 1/2 times 25.5 squared over 0.09 times 9.8, and we would find that this distance would be 368 meters. So d2 is 368. So this gives you hopefully a helpful quick example to show you a situation where you have conservation of energy, but you also have to incorporate the work that's been done by a non-conservative force, the work that's been done by friction.